All right, let's take a look at our lesson for today on infinite limits and limits to infinity. First of all, I really want to talk to you a little bit about how limits are really in two different categories. So I really want to come over here, and there are different techniques. So let's just come over to the side and let's make ourselves a little chart. Okay, so I'm going to call the limits that we have been doing are the normal limits. Right, the normal, that means x is going to some kind of a number. Okay, these are normal limits. And you recall with the normal limits, we have three things that can happen. Like number one, you plug the number in, or, plug number in, get a number, you're done, right? That was type 1, the type 1 limit. Type 2, if you remember, you plug a number in, you get an indeterminate form, 0 over 0, infinity over infinity. That means keep going. And in that lesson, we talked about the 4 different ways to keep going. I'm not going to write it down just for space sake, but somebody remember, what is the one way we could try to keep going of the 4? One of the 4. Factoring. Factoring is one of them. What's another way of the keep going? Conjugate. Multiply by the conjugate over itself. That's like a clever form of 1. That's the second one. There's 2 more. What's another thing we could do to keep going? Yes, those complex fractions, those lovely complex fractions, we fix them, we take them out of complex form, find a common denominator, all that business. That's 3. There's one more that we do when we keep going. The trig properties. Those are the 4 things we do and we keep going. Okay, and that we talked about that when we were doing a few lessons ago. Number 3, these are normal limits. Number 3, we plug in a number. We get a number over 0. And when we get a number over 0, that means the answer is going to be infinity, negative infinity, or combo, which is D and E. And so remember, for that technique, we would go 1/10 on either side of the x value. Remember that, to see where we're going on the coming from the left, coming from the right. So we would go 1/10 on either side of x value to determine the sign, positive or negative. Okay, so that's normal. Those are normal. When we do limits to infinity, we don't use these techniques. Okay, we don't use these normal techniques. We have different things to do, and that's what this lesson is about today. So I'm going to put over here, and as we start going through things, you can fill in this side. These are limits to infinity. These are different techniques. And I think that may be one reason why students get frustrated. I can't even spell infinity, sorry, infinity. Because they're thinking that the techniques they've been trying are going to work, and they don't. These are completely different. It's like a different little animal, if you will. They're different. Okay, so I want you to go into this lesson with the idea that this is a different kind of limit, and we work them differently. Okay, are we okay with that? So these we do not work like the regular normal limits. These are different. So with that in mind, let's take a look at our lesson. Okay. So we are going to be dealing with vertical and horizontal asymptotes. There is the definition of vertical and horizontal asymptotes. And by the way, our formula quiz will not include this lesson. I need us to understand that. The formula quiz coming up will not include this lesson. Now, definition of vertical and horizontal asymptotes are on formula quizzes, but not the next one. So, what's that? Maybe next class period. I don't know. We have to look at your syllabus, because I can't keep them all straight. So let's talk about these two definitions. Let's talk about how they work. A problem that you might have, it might say, use the definition of vertical asymptotes to find vertical asymptotes. All right, so with vertical asymptotes, we need pre-knowledge. We need to think about, our pre-cal. So if you remember, what do? We like factor the denominator, right? I'm just making something up. So in this case, our, vertical asymptotes would be at 2 and -3, right? We set the denominator equal to 0. Remember that from pre-cal? So our vertical asymptotes, in this case, the vertical asymptotes would be x equals 2 and x equals -3. And what we do is we actually do the limit. That's what the definition tells us. So we know what they are. You need to know what they are before you go about trying to use this definition. Then if we're just going to look at this one right here, and in fact, I think I have an example. Yeah, I have an example on this, so I'm not going to go through how the example works. I just need you to know that we would do our pre-cal, figure out where they are, and then do the definition. For horizontal asymptotes, like I said, I have an actual example that we'll go over. You would just do the limit to infinity, negative infinity. So that would show horizontal asymptotes. Okay, so that's the definition. These are common limits. So these are the things you're going to be using when you do limits to infinity. It's these formulas that you would have to know, right? You would have to know them. So how in the world are we going to know all of this? Well, if you remember what the graph looks like from, pre-cal and algebra 2, the graph of e to the x looks like this, right? That's e to the x. So if you knew the graph for e to x, then you would know that as x goes to negative infinity, y goes to 0. And as x goes to infinity, y goes to infinity. I mean, you would know that from the graph, right? Same with natural log. So with limits to infinity, graphs are important. Graphs are important with limits to infinity. For natural log, if you recall, it looks like this. There's an asymptote on the y-axis. So as we're headed to 0 from the right, our limit would be negative infinity. As we head to infinity, it's going to get bigger and bigger. Our y value get bigger and bigger, and we're at infinity. So those are some common limits to infinity. You just add those in the column over there when we were going through how are you going to do limits to infinity? Well, you need to know graphs. That's a good thing to write there. You need to know graphs. This one is highly significant. This one that I am highlighting. This guy is a really big deal. A lot of our work is around this concept. And I want to talk about the concept, and then we'll talk about how it's used. So if you can imagine that this denominator, and it doesn't have to be just to x, I mean, basically x to the n, to anything. X to anything. That denominator is going to grow without bound, okay? It's going to get larger and larger. So therefore, the fraction itself is going to get smaller and smaller, and it's going to tend to 0. That is a really big concept for us. Okay, when we're doing limits to infinity, this one that I've highlighted is a big deal. So a lot of limits use that concept. The other arctangent is also a graph, and I'll just graph it for you. This is a graph that you should hopefully remember. Well, let me graph it down here. So we'll go over here. So the graph of arctangent looks like this. Oops, let me get it nicer. Okay, sorry, it's terrible, but it has horizontal asymptotes at pi over 2 and negative pi over 2, which is why when we're headed to negative infinity, arctangent's limit is negative pi over 2, and we're headed to positive infinity, arctangent's limit is pi over 2. So all of those infinite limits we've got from graphs, except for that one. right? So graphs are going to be important to us with infinite limits. Okay, bless you. So let's look at this. I'm very visual, so I love these pictures. It really helps me. So limits at infinity and infinite limits. Okay, we're looking at both the kinds today. Limits at infinity, this is the number over zero business. These are from our normal limits. We've actually already talked about how to do these limits, as x goes to, right here. So this would be like this one. We're headed to, where are we? No, this one right here. I'm mixing the wording up. This one is our normal. This is our normal limits. This is the number over zero business. When x is going to a number 2 or 5 or whatever, and the y value gets really big or really small, this is the number. When we're working algebraically, this is the normal number over zero business. These are the new ones. These are as x goes to negative infinity, as x goes to infinity. These are limits to infinity. And these are where we are looking at horizontal asymptotes. These are horizontal asymptotes. See how as it's heading this way, it's going to slide along that horizontal asymptote? Where our normal ones that we were doing, those were vertical asymptotes. And you don't have to memorize that. That's just a visual picture of what's going on. Okay? So now let's look at these here. These first two are from our normal business. This is the number over zero, guys, which we did before. Okay, so I'm going to split it. I'm just going to automatically split it and use a limit law. Limit as x goes to 3 of 1 is 0. Limit as x goes to 3 of x minus 3. Oops, sorry. Limit as x goes to 3 of 1 is 1. Limit as x goes to 3, so 3 minus 3 is 0. So this is the number over zero business. Okay, so what do? This means there's a vertical asymptote at x equals 3. That's what this means. There's a vertical asymptote at x equals 3. Okay, so let's figure out what we're going to do to do this limit. This is where we go. Let's see, 1, 2, 3. So we want to go 1. That's our vertical asymptote. We want to go 1/10 on either side to test this. So I'm going to do like on this side, I'm going to do like 2.9. So I plug in 1 over 2.9 minus 3. This gives me a negative number. And so coming from the left, it's going to negative infinity. Okay, so if I was drawing the graph, it might look something like this. Okay, so now we're going to go on the right. We're going to do 3.1. So we do 1 over 3.1 minus 3. I get a positive number, which means that's infinity. And if I was going to draw the graph, it would, look something like this. All right, so when we're doing limits and we hit upon a vertical asymptote, they want us to tell them what direction the y value is going. That's what they want. When the direction is mixed like this, we say D and E. Only when the direction is mixed. Since this direction is mixed, we would say, therefore, D and E, since left side goes to negative infinity and right side goes to infinity. And that would be our reason. Remember, whenever you say D and E, you need to tell me why. Just saying D and E is not enough. And this is a regular? This is the regular. This is type 3. If we go over here and look at our list, this is a type 3 limit where we get a number over 0. So our answer is going to be infinity, negative infinity, or a combo. And a combo, which is what we have right here, means D and E. That's regular. Okay? All right, how are we on this one? Okay, this cotangent one, I would plug in a 0, cotangent of 0, and that's not defined. So this one would be much easier. So the easiest way for this one, easiest way is to graph cotangent theta. I'm sorry to say that. It's the easiest way. So you probably thought all in Algebra 2 pre-cal, why are we graphing so much? Why are we graphing so much? This is why we graph so much. It's because of calculus. Okay? So do you need to know how to do 4 transformations of trig function? No, we're not going to do crazy graphing like we did previously. No crazy graphing. This is just basic graphs like cotangent. So the basic cotangent graph has an asymptote at 0, and it comes out to pi. It has another asymptote at pi. And if you remember, it faces the opposite way that tangent does. It goes like this. Okay, that's what it looks like. And over here, it would go like that, and so forth. It goes on forever and ever. So if I am headed to 0 from the right, so we're just going this way to 0 from the right, what is my y value headed towards? Infinity. So this limit would simply be infinity. Don't put equals infinity or arrow, just write infinity and box it in. When you box something in on the AP test, that's what we look at. We look at your boxed answer. Okay, we look at the work that you do, and then we looked at the answer you box. If you don't box, then we just keep looking at your work to figure out what you think the answer is. You know what I'm saying? Okay? All right. All right, so we good?
What's an example of cotangent ending up negative?
So if this had been the limit as theta approaches 0 from the left of cotangent, then this is where it would be going down. That answer would be negative infinity. Because it's headed from the left, it's going down. Does that make sense?
Yes.
Okay, wonderful. All right, so let's go to our second page. Here we've got a graph. I love the graphs. So we're going to figure out what's going on. We're going to use the graph to answer these questions. So we're going to 1 from the left, and we're going to infinity. Don't equal, just put infinity box. Okay, we're going to 1 from the right, and that's also infinity. So those are the one-sided limits. Going to 1 is a two-sided limit. Where is the two-sided limit headed? They're both going the same way, aren't they? So the two-sided limit is going to also be infinity. That's what it is. Okay? So now let's go to 2 from the left. So 2 from the left, we'll just change color. So 2 from the left, there's 2, there's the left. 2 from the left is infinity. 2 from the right, this is one where we're going down, so it's negative infinity. So what do we say about this full limit then? Doesn't exist. This one does not exist, and please don't ever say does not exist without saying why. Does not exist because what?
Left side limit, the right side limit.
Don't equal. Yeah, you could actually just say that. You could use the mathematical notation. The limit as x goes to 2 from the right of f does not equal the limit as x goes to 2 from the left. You could write it like that, or you could write it in words, whatever you're more comfortable with. You could say does not exist because the two one-sided limits don't tend to the same direction, or they don't equal the same number, or there's a lot of ways you can say it. Okay, how are we doing? All right, let's look at number 4. So on number 4, we're going to focus on the x, because that's, x is going to negative infinity. So I want you to think about, as this location right there grows bigger and bigger and bigger, what is going to happen to this whole fraction? What's it going to tend to or go to? 0, right? Well, if you think about fractions like 10 over 100, 10 over 1,000, 10 over 10,000, 10 over a million, that's going to be a really small number, right? 10 over a million is really little. It's going to get so close to 0, we're going to say that it is 0. So that turns to 0. So then what is the limit of a constant? What's the limit of 2? 2. The limit of a constant is the constant. So our answer is 2. Okay, do you see how in this one, so let's talk just real briefly. I want to just try to keep us together. So the techniques for limits to infinity, so far, we've used graphs and we've used this special limit. So I'm going to write over here, these are our limits to infinity techniques. Okay, number 1, graphs. And number 2, that special limit goes to plus minus infinity of 1 over x equals 0. That's a really big deal. Okay, really big deal. Okay. So that's adding to our list. All right, so, okay, this is, so there will probably come a time when you can look at this problem and tell me what the answer is without doing anything. Okay, there probably will. We're not going to do it like that now, but there probably will come a time when you can do that. What we do, the technique that we use is called the algebraic technique that we use is we multiply, just write this up the side, we multiply by 1 over x to the largest exponent over 1 over x to the largest exponent. That's the technique. And in doing this, we're going to be using limit x goes to plus minus infinity, 1 over x is 0. I mean, that's why we're doing this technique, because we're going to use that limit, which we just said is a really big deal, because it is. All right, so I'm going to multiply by 1 over x to the 4th over 1 over x to the 4th. That's what I'm going to do. That's the algebra technique for this. So the limit is x goes to infinity, 40x to the 4th over x to the 4th plus 4x squared over x to the 4th minus 1 over x to the 4th all over. So see, I distributed 1 over x to the 4th to all the things on top. Now let's do on the bottom, 10x to the 4th over x to the 4th. You betcha. 8x squared x to the 4th. So let me just get it written, and I'm just going to let you catch up. I'll just let you catch up. So I'm just distributing 1 over x to the 4th to all those terms in the numerator and all the terms in the denominator. Okay, how are we doing? We're close? Still, okay, so that's good, that's fine. You're like, Dr. Wright, this is the first time we've seen something like this. Slow down. Got it. Okay. So what I'm going to do, are we all okay? What I'm going to do is any of those fractions, any of the fractions that do use this, any of the fractions that use this, I'm looking at the fractions one by themselves. Please don't look at it as a big whole. One by one. I'm going to circle it because it's going to turn to 0. That's what I'm going to do. Okay, this is going to turn to 0. So I'm going to circle it. And actually, I'm going to circle it with pink so that it stands out. To me, when I circle it, that means I just made it 0. That helps me. I just made that 0. Do you see another one that's going to be 0? The one right below it. That's going to be 0. Okay. Now, the middle top one, I want you to imagine what it looks like simplified. I'm not going to go and rewrite it, but what would that look like simplified? 4x squared over x to the 4th. It'd be 4 over x squared, right? Is 4 over x squared going to go to 0? It is, but I'll write it up here. So 4x squared over x to the 4th reduces to 4 over x squared. Remember I was talking about that special limit? As long as the top is a number and the bottom is x to any power, it's going to go to 0. So this one's going to 0. What about the one directly under it? Yep, it's going to 0. Now, what is x to the 4th over x to the 4th? It's 1, so I'm going to say that's 1 and that's 1. All I have left are the numbers 40 over 10. And my answer reduced is 4. So my answer to that is 4, using that algebraic technique. Okay. Are we okay? Okay. Very good. 6 is a little stinker. I'm going to save it for last. I know you're like, oh no, let's do it now. Let's look at the horizontal and vertical asymptotes and then we'll go back to it. So, horizontal asymptote, the definition would be limit as x goes to infinity of x squared minus 9 over x times x minus 3. Okay, I'm going to go ahead and multiply out the bottom just so that our technique is okay. So this is x squared minus 3x. Okay, so I'm going to use the technique that we just talked about. I'm going to multiply by 1 over the biggest over 1 over the biggest, 1 over x squared over 1 over x squared. Are we okay with that? Okay, so we have the limit as x goes to infinity. I've got x squared over x squared minus 9 over x squared in the numerator. I've got x squared over x squared minus 3x over x squared in the denominator. Okay, let's identify some fractions that we can circle and ignore. I don't want to hurt their feelings, but they're turning to 0, so I'm going to ignore them, okay? Do you see, there's 4 fractions that I'm looking at. Do you see one fraction that I can circle and ignore? 9 over x squared, that's 0. Do we see another one? 3x over x squared, that's going to 0. Great. And x squared over x squared is 1, and x squared over x squared is 1. So my limit is 1. 1 over 1 is 1. That means, therefore, there's a horizontal asymptote at y equals 1. That's how the definition of a horizontal asymptote works. Yes?
It doesn't matter if there's an x in the top.
No. I'll be perfectly honest. I'm just being lazy and not simplifying it. Because that's really 3 over x, right?
Wasn't the special limit 1 over x to the power?
It is.
And that's not to the power?
This one simplified is 3 over x, so it matches the special limit.
But that one had it was to the power.
No, let me show you. I put it in there, but the n could be 1,
Oh,
right? It's okay. The n could be 1, it could be any number. I just put it in there because usually students get confused, like 1 over x squared. What? That doesn't match the pattern. But it's okay. Are we okay? Okay. So, are we okay with horizontal asymptotes? Is this a yes?
yes.
Okay. So, to do vertical asymptotes, I need to simplify this. Because if you remember from your previous math, sometimes there's a hole, right? Remember that? Sometimes there's a hole. Is there a hole here? Yep, right there. So there's a hole at x equals 3. Now, they're not asking us about the hole. We don't need to do anything about it. We just know that it's there. So this actually simplifies to x plus 3 over x. Okay, so when I find my vertical, remember with vertical asymptotes, you have to do pre-work. You need to know what it is you're looking for. When I set the denominator equal to 0, what is my answer going to be? The denominator, the bottom. X equals 0. That's a vertical, there's going to be a vertical asymptote at x equals 0. Okay, now we know what we're doing. So the definition says, do the limit as x goes to 0 from either side. It doesn't matter. Okay, where are we okay?
Why did we do that up there?
So,
X equals 0.
okay. So, are we okay with this being the function, the simplified function? Everybody okay with that? Okay. So we need to think back to pre-cal. How did we find vertical asymptotes in pre-cal? What did we do? We set the denominator equal to 0, right? The denominator is x. X equals 0. Up here, when I made up a problem, remember that? Right there, I set the denominator equal to 0. Remember that made up problem? X equals 2, x equals negative 3. Why? Because I set the denominator equal to 0. That's how you find vertical asymptotes. So you have to use your pre-cal knowledge to find where this little beast is before you can prove that it's there. Is that, you with me? It's pre-work. Okay. So that's why x is 0. So the definition tells me, and our simplified one was x plus 3 over x. X plus 3 over x. Okay. So when I do 0, I mean, basically it would give me 3 over 0, which we know that's the third kind of limit, right? Type 3, there's a vertical asymptote there. Well, yes, there is. That's why we're doing this, right? We want to go from the right. So I'm going to do my number line thing. So I'm right here. I want to come from the right. So I want to do 1/10. So 1/10 plus 3 over 1/10. That gives me a positive number. So therefore, this tends to infinity. Therefore, x equals 0 is a vertical asymptote. Yeah, you can think of it as 0.1 if you want to. I'm doing 1/10 from the right and I just need to do from the right. You need one or the other, you don't need both. So that's how we use the definition of the vertical asymptote. Are we okay? Yes? Okay, I saved the best for last. Y'all are going to be so excited. Okay. All right, just let's talk about this. Let's talk about it. So the reason this one is a problem is because there's a radical. I'm just going to write that down. This one has an issue because of the radical. Remember, a radical, that's the square root business. That's a problem. I'm just going to throw it out there. It's a problem. It has to be attacked a different way so, some students are like, it's been so confusing so far. Why are we doing this? Why? This is even more confusing. Which I said, limits to infinity are challenging. They are. But the great thing is, it's not like you're going to have a whole test with only limits to infinity. That wouldn't even make any sense. You may have one problem or two problems or something. It's not the end of everything. It's harder. So let's see if I can think of an easy way to explain this, because I'm going to have to go into some math theory. Sorry. Okay. We need to talk about the square root of x squared. That's equal to the absolute value of x. That's really troubling to many of us. This is the whole reason this problem is hard, right here. The whole reason. Because the definition of absolute value of x is x when x is greater than or equal to 0 and negative x when x is less than 0. Right? That's what it is on our formula sheet. That's the definition, the absolute value. And this is why you need it, because of this and other reasons. This is one. Okay. So with that being said, as I look for, I'm going to multiply by 1 over the biggest over 1 of the biggest. That's what I'm going to do. This is really kind of messed up because I got x to the 4th in the numerator and the square root of x to the 8th in the denominator, which is really x to the 4th. The square root of x to the 8th is x to the 4th. Well, the absolute value of x to the 4th. Okay? That's what it is. So we'll just write that up here to remind us that the square root of x to the 8th is the absolute value of x to the 4th. I mean, that's what it is by the rule that we were just talking about. Okay? So when I multiply, I've got to multiply by 1 over x to the 4th over the square root of 1 over x to the 8th. And you don't have to put the 1 inside the square root. I don't know, sometimes that bothers students, sometimes it doesn't. It's fine. So that's what we're doing. So let me rewrite and let's do all our multiplying. Right? We've done this before. We know how to do it. 40x to the 4th over x to the 4th plus x squared over x to the 4th plus 5x over x to the 4th over. And this is actually, let me throw in the absolute value. It's actually absolute value x to the 4th, right? Because that's what we have to make them match. We have to make them match. Now I'm going to get inside the radical, and I'm going to multiply inside the radical. 64x to the 8th over x to the 8th plus x to the 6th over x to the 8th. Okay, I'll let you catch up with me. Now I want you to look and identify the little fractions, the little baby fractions that are going to go away. They're going to turn to 0, and we're going to circle them. Okay, can somebody tell me one little baby fraction that's going to go away? 5x over x to the 4th is gone, it turns to 0. Can somebody tell me another one? You got it. That's going to turn 0. And then I have one underneath the radical that's going to go to 0. Yep. That one's going to go to 0. Okay, so here's the weirdness. Here's the weirdness. We're going to negative infinity. We're using the negative side. So when I work with this, I only want the negative side, and I'm going to, this is just to save me work from rewriting. I'm going to turn that, bless you, to negative. That's really the only weirdness that we have, is that one thing. The rest of it is just, I mean, and plus it's a radical, that's weird. Okay, so this goes to 1 and this goes to 1. So my answer is negative 40 over the square root of 64. Which is negative 40 over, let's see, square root of 64 is 8, which is negative 5.
Why did you make the first negative or negative?
That is because of this definition up here.
Is it because the x's cancel out?
No, it's because x is smaller than 0. The x that we are working on is smaller than 0. This negative infinity is smaller than 0. So we have to use the alternative, the other piece. See what I'm saying? If I ignored, if we were going to infinity, the answer would be 5. If we were going to infinity, the answer is 5. But because we're going to negative infinity, the answer is negative 5. That's the weirdness of it. That's the thing that drives students crazy. I'm not going to lie. This is like the hardest one. But if you can kind of embrace the fact that we're using that definition of absolute value of x, maybe that would be helpful.